former member of NOVAC before he moved out of the area, and I guess former president of NOVAC.
91, I think it was,
Oh.
92. Long
Way
time
back
ago.
when. Moved to Fredericksburg
Mhm.
and is now active in the club down there, the Rappahannock Club. Also very active in telescope automation. And we're going to hear this afternoon about the automated observatory they have, which uses some of the Explore Scientific equipment, I guess, as a place to prove it out. But I invited Dr. Wasiuta specifically to talk about an optometrist or ophthalmologist?
Optometrist.
Optometrist
Yes,
view
that's correct.
of visual
Yeah.
astronomy and especially some of the opinions, myths, theological debates about vision and astronomy and what you can actually see, the best way to observe, to avoid, to maintain dark adaptation and other aspects of using your eyeballs and not cameras through the telescope. So with that, I'd like to introduce Dr. Wasiuta.
Thank you, Alan. It was very nice. Yeah, I'm really happy to be here. This is a topic that I could probably sum up in just a few minutes, and then we can get into the details afterwards, because we're all very familiar with visual astronomy. We've been using our eyes for many years at this activity, and probably most of what I'm going to be telling you about today you've kind of figured out on your own already. But it's kind of neat to get into some of the research that's been done about dark adaptation and using our eyes for a task that's very admittedly not what they were designed to do, and yet are still quite surprisingly good at visual observing in the dark. So with that, we could just go through some slides. I don't want to spend too much time on the front. Are we? Microphone? Oh, it's just for the camera, yes. So what I'll do is, sorry?
What's in your right hand?
Yes.
Go on your hip or
Yeah, I put it in my hip and I turned it off last time. Yeah. All right. So just basically, my interest, as Alan was saying, was primarily visual astronomy. A long time ago, I got into deep sky observing, and then telescope making, and then astrophotography. Pretty much the same path a lot of us probably took. And now I'm involved in a remote observatory that actually Jerry is going to be talking about here. You can raise your hand, Jerry, a little bit later this afternoon, that we have in the backyard of my house, and it's a remote facility with a 6-inch telescope. But visual astronomy has always been my love. I think that's where I started, and what I want to do is just talk a little bit about, go ahead, next slide, just go through these quickly. I'm an optometrist. My claim to fame, I guess, is I've been president of a couple of large astronomy clubs and got to meet a very large group of interesting people like yourself, and had the privilege of serving the amateur astronomers where I've lived in the past. I've gotten to meet several prominent, interesting people over the course of my astronomy career as well, which I'll go into a little bit later. I developed I guess if I have a claim to fame, I developed the Starpoint astigmatism correcting lens, which was out in the 1990s as a little article in Sky and Telescope about it. And I actually made over 200 of those things. What it did is corrected a person's astigmatism so that you didn't have to wear glasses when you observed. And one night, after placing the ad, I got a call from my wife was in the kitchen. She answered the phone, and the phone rings, and my wife says, "Oh, Myron, there's some guy named Arthur Clarke on the phone." So I said to my wife, "Arthur C." No, I went to the phone. I said, "Arthur C. Clarke." He says, "Guilty as charged," in his deep voice. So, long story short, he got one of the lenses because he has a lot of astigmatism. And I happen to have a first edition 2001 Space Odyssey, which I signed. I'll pass around. I had to send it all the way to Sri Lanka to get that. Next couple of slides, you can keep going. So this is our eye, basically anatomy. A lot of people think that the lens, which is actually inside of our eye, is what focuses light to the retina, which is the back part. This is where light is detected. It's not the lens. The lens actually plays very little role in focusing. The primary, most important refracting surface in the eye, anybody want to guess? Cornea. Specifically, what's in front of the cornea? The precorneal tear film. Remember that, okay? It's a very thin, micron-thick layer of moisture that is the primary refracting surface. If that thin layer is not intact, the quality of your vision is reduced in terms of clarity, which is our term is acuity, and in terms of contrast sensitivity. Both those things are important for night observing. The best thing you can do to keep your night vision intact, of course, other than dark adapting, which we'll talk about in a minute, is to keep that precorneal tear film healthy. And we'll talk a little bit about that shortly. But anyway, so as light goes in, it passes the cornea, goes into the front of the eye, which is filled with liquid. This is the only part of that where there's actually a liquid. This is called the anterior chamber, and it's clear. Optically, it does nothing to the forming the image. Then light passes through this structure, the lens. The primary purpose of the lens is to allow variable focal positions of your eye. So if you're looking in the distance, the lens is in one shape. When you read, these little muscles right here, called the ciliary body, are attached to the lens via these things called zonules. They're strings, basically. And these muscles contract and flex in and out and change the shape of your lens in your eye so that your focal point changes from distance to near so you can read. That's really the main purpose of the lens. It's not really to focus light on the back. That's primarily determined by the shape of your cornea. Your prescription is determined, whether you wear glasses for nearsightedness or farsightedness, by the shape of the curvature right there. So the lens does not do much in terms of help you with focusing other than changes the focus. It does do something later on in life that can reduce the quality of your vision in the form of a cataract. So when you get cataracts, this is where they're at, right in here. So then the light passes through the lens and it goes into the vitreous, which is the largest volume area of the eye. And we're talking about an inch from here to here, okay? So maybe an inch and a quarter. So the vitreous is a source of a lot of things that we see in our daily life, meaning when we're looking at the sky, you can see little floaters and cobwebs and things. That's cellular debris, actually, in the gel of your eye. But again, it doesn't do much to actually focusing. It's just there. It's inert. Yes?
You said cataracts are on
In the lens of the eye.
the cornea.
No, they don't replace your cornea. They replace this structure right here. So they go through the cornea using an instrument that is a vacuum tube, basically. That is an ultrasound probe. It vibrates very, very quickly. And it just shatters the crystalline lens into thousands of little teeny pieces. And then it gets sucked out of the eye through a little opening in this area right here. All right? And then through that another small opening, they insert a new lens. It's called the implants that some of you might have, actually. And those implants in the old days used to be solid, rigid, in which case you needed a big incision, 7 millimeters and plus. But now they have foldable implants that are curled up into a little tiny straw, basically, and they inject them into the eye, and then they open up, kind of like a sail on a spacecraft, unfurling its solar panels. And that then has the optical power appropriate to focus to the back of your eye, and they calculate that. And and they're very accurate now with that calculation. We're getting to the point where almost people are walking away from cataract surgery pretty much with 20/30, 20/25 vision.
I've had cataract surgery in both my eyes. I've had 2015 one eye, 2020
But they
Mhm.
no longer attach to the lenses, correct? So
Correct. That is correct. So they leave this structure intact here. There's a bag, we call it. It's a cellular membrane, a sac that the cataract the lens is in. They leave that too. And so they put the new lens in there. But in most cases, because of insurance reasons, they don't cover the cost of doing the premium lenses, which are the ones that can, one way or another, act like a bifocal. And so those lenses work a different way. And some of those, they do actually kind of attach in a certain way. And there is some translation of the lens in the eye, but those lenses, we're not there where we would like to be in terms of near vision on that yet.
Could you just describe the function of the contact lens then?
So a contact lens is fit to the curvature of the front of the cornea, and it replaces the curvature of your cornea to a new curvature that has the proper prescription to focus light on the back of your eye. And that contact lens is much less than a millimeter thick in most cases. But the front surface is shaped to allow optically light to focus now to the back of your eye. So that's what it just replaces the front surface curvature. It changes it to the value that's needed to focus light on your eye, the retina in the back.
Can astigmatism be corrected when the lens is replaced.
Yes. And that's one of the premium type of lenses that are out there.
But that means they have to X and Y or.
Yes, it's rotationally sensitive. So when they put those in there, they got to rotate the lens, just like my store point lens a long time ago. You had to rotate it in the eyepiece to get to that signal. They do the exact same thing in the eye. The surgeon will stick it in there and they'll move it around so that the lens is oriented properly. Bill?
Have there been any fanatic astronomers who have gotten eye surgery to help the eyes?
No, not that I know of. It comes into medical legal type of issues there. But there is I get a lot of asked questions about what type of lens is best for me. I'm an amateur astronomer. What will give me the best possible nighttime vision? And that's a hard question to answer. There's a lot of answers out there. It kind of depends on the individual, how seriously you want the best possible vision for night. If you want the best possible vision for night, your best bet is doing 2 monofocal single vision lenses for distance, and then you're going to be wearing reading glasses. And that's the best way for night vision. But in real life, how much time do you spend at night? Do you want to really have the convenience of maybe having freedom from reading glasses? That's a great thing. You might want to consider the next best thing, which is a diffractive, not a bifocal, but a diffractive lens that's, the common term is symphony, the symphony lens. And what it does is it uses diffractive to expand the clear range of focus so that you get a bit of help up close without sacrificing your distance vision. Because the next step up is a diffractive bifocal, which then produces 2 types of images, a distance one and a near simultaneously. So at nighttime, you got glare and halos that you might have to deal with. You don't get that with the symphony lenses, hardly at all. So,
You're saying diffractive, so is that holographic?
not holographic. It's a diffractive. So they have a series of ridges on the lens, and they use actually the principle of diffraction to bend light to form 2 images.
Sounds like Cornell.
It's kind of like a Fresnel. It looks like, when you look at it in a microscope, it looks like those old lighthouse lenses that you used to see, those big Fresnel lenses. It's a clear zone in the center. Then there's a series of rings, concentric rings that get closer and closer together as you get further out in the periphery. They're not opaque. They're transparent. Yep. Those are called diffractive optics. And the one and the diffractive optics can be used to either give you simultaneous distance and near, which is the bifocal diffractive, or to correct optical aberrations and expand your clear range of focus in a monofocal lens. That's called a symphony lens.
These are all contact lenses?
No, these are implanted lenses in your eye. We're talking about cataract surgery here now. Yeah, to kind of get, since a lot of us are at that age where that might be an issue. Yeah, yeah. So I'm happy, if y'all want to contact me, I'd be happy to talk to you about what is the current latest, greatest stuff out there. So, but talk with your eye doctor. Talk with him or about your interests, and then try to make a decision. So at the very last part of the eye is the retina, and that's where the rubber meets the road, as they say. That's the part of the eye that detects light and then sends it to the brain via the optic nerve. So there's millions of photoreceptors in the eye. These are light-sensitive cells that fall into 2 classes, rods and cones. We all have heard about that. And they're wired together in a way that they converge into an area of the eye called the blind spot or the optic nerve. There's no cells, no photoreceptors there. So you got a blind spot in your eye. That's where the optic nerve is. And then all those convergent fibers, the millions of them, then go shoot out of the eye back towards the brain, where eventually they reach the visual cortex in the back and vision is perceived. So, and a lot happens between here and the brain. A lot. Okay, let's go through these slides. I don't want to. Yes. So the size of yes. So the diameter of the highest resolution, the cones in the fovea, they're about 8 microns in diameter. That's when they're packed together really tight. So we got about an 8 micron system in our back of our eye. Yeah.
Are you going to tell us about that macula later?
Yes, I got a bunch more slides when we get to that. Yeah, I'm going to show you the diseases of the eye as we go through here, and then we'll talk about at the very end a few of Roger Clark's. If I don't get to it, buy this book if you're into deep sky observing, because it's a gem. It really does go into a lot of what I'm talking about in much more detail than I can cover today. Okay. Let's keep going. So this is everybody's the big E. Okay, what does that mean? 20/20 vision. So 20/20 vision means that your eye at 20 feet can resolve 1 arc minute structures in a letter that is 5 arc minutes tall. And that's called 20/20 vision. If you have 20/40 vision, that means that you have vision that is only half as clear as normal, which means you have to go into 10 feet to see a letter that a person with normal vision could see at 20 feet. So 2040 is worse than 2020. 2010 means that you can see something at 20 feet away that a person with normal vision has to go into 10 feet to see. Okay, does that kind of make sense? Okay, let's keep going. Next. So visual acuity, as we can imagine, this is out of my physiologic optics book, by the way, which is a lot of my slides come out of that. They also come out of Roger Clark's book. Visual acuity declines with age. We kind of know that, but why? Why does it decline with age? Mostly because of optical imperfections in the eye. We have two optical systems. We have the lens and we have the cornea. And when we're young, those are nice and clear and good health. As we get older, they deteriorate, and as they deteriorate, our vision goes down. And so our acuity begins to go down. So by age 80, what this means is the Snellen fraction, 0.5, means you're about half of what you were when you were young. So that's around 2040. So the average vision of an 80-year-old healthy eye is about 2040. That's kind of what that means. And then also, this is an important graph here too. So when our eyes really do not have very, very clear vision in much area. It's just straight ahead where you're looking. That's because our eye is not designed to give a perfectly clear vision way out to the sides. We sacrifice clarity for other things, like detection, light sensitivity, motion detection. All those things are important for survival, and we give up resolution to gain those. But the area that we don't give up resolution is in the very center. And that's the fovea centralis of the macula. But as you move away from that, as you look away from something, just think about it. If you're looking at a word in a book and you look 3 or 4 words away from it, can you still read that first word? Probably not, unless you know what it is, because our acuity declines with eccentricity. So by 30 degrees out, we're less than 0.1, which is like 2200, 10 times worse. So when you're looking through a telescope, we all know about something called averted vision, right? You're looking away from something to appear brighter, and we'll talk about why in a minute. But what you're doing also is you're sacrificing resolution the further away you look. So there's a sweet spot in there, and I can't tell you where yours is, unfortunately. There's no magic there. You have to figure that out on your own by trial and error. But there's a gain in sensitivity the further away you look, but a corresponding loss of resolution. And somewhere those two curves meet, and that's your sweet spot, and that's where you need to offset your fixation to get the best vision. Just takes practice. You just got to get out there and do it and see. Okay, let's keep going.
That's not a typo. That research was done in 1894.
That is not a typo. Some of this stuff is still valid today. Some of this stuff goes back a long way. Some of Roger Clark's research goes back to the 30s in there. So anyway, visual acuity depends on a lot of things. Obviously, ametropia means nearsighted and farsightedness. Something that a lot of people think of. Our eyes have optical imperfections that are high-order aberrations, like coma, like trefoil, like spherical aberration, okay? Like off-axis astigmatism. All these things that you see in your telescopes, we got in our eyes too, and they can reduce vision. And they're not things you can all the time correct in an eye exam. So some of us wear glasses to correct our nearsightedness or our farsightedness or our astigmatism, and we still don't see as well as the guy next to us because that eye has focused better because it has less high-order aberrations. And again, the degree of transparencies and the health of your eye. The health of your retina, and that's something you have some control over. Your lifestyle is very important. If you do things that reduce quality of lifestyle in terms of healthy, unhealthy things, the quality of your vision can suffer. The biggest thing, and a lot of us are guilty of this, I know, smoking. Smoking has a detrimental effect on the quality of your vision, particularly later in life, because of the toxicity of the carcinogens in the smoke are concentrated in the areas of your body that are the most metabolically active. And guess what one of the most metabolically active areas of your body is? Your fovea and your brain. That's right. In terms of vision, your fovea. So that's the center of your retina. That area is bullseye for the bad effects of smoking. And that decreases contrast sensitivity and decreases clarity. And then the density of our foveal cones. We had a question, how dense are they? On average, 8 microns. Some of us have 6 micron cones that are packed together that tight. Some of us only have 10 microns. Stephen O'Meara, right? His vision is legendary. When he can see things through a telescope that none of us could ever see, because he's gifted with a fovea that is just super, super high resolution packed rods and cones. Or cones, actually. There's no rods in the fovea. So anyway, okay, let's keep going. So just quick, we can go through these quickly. This is 20/20 vision, okay. This is what 2200 looks like, 2400. 20/70, okay, legal driving in Virginia. I put this up here, okay. Legal driving in Virginia. You only need 20/70 vision to legally drive in Virginia. Yeah. Okay, let's get going. All right, so these, we already talked about this. These are the various orders that we go through. Let's go next slide. This is cool here. And then color vision. This is another thing that is so variable with people. Not only clarity of vision, but our color vision is very subjective between individuals. I see this all the time in the exam room when I'm doing color vision charts. We got the book, what number is this? And you go through there, and some people miss numbers that other people see and all that. And it's really cool. So basically, our color vision is due to the fact that we have three cone systems in our eye. So the cones see color, the rods do not. The cones have high resolution, the rods have low resolution. The cones have low sensitivity to light, meaning high threshold of detection. The rods have low detection. They're very sensitive. So they're, in a nutshell, the basics of the two kinds of cells. But color vision is due to the cones. And there's three kinds of cones, the red, green, and blue, or long, medium, and short wavelength sensitivities. And these are their peaks, basically. Don't really need to know that too much. But interesting, people with really good color vision can differentiate if you put two hues next to each other that are just very, 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 very similar and use a monochromatic light. They've done this to see how sensitive we are to color differences. There's some people can detect 1 nanometer of difference, where others 4 times less, only 4 nanometers, which is still, 4 nanometers is still pretty mild change there. But that just gives you an idea, all right? Now, color vision issue, we know about color blindness. Color blindness occurs mostly in men, but it does occur in women. Color blindness is not color blind. You do see color. If you have the most common kind, it's red-green deficiency, meaning reds and greens look the same, but it's because you don't have that red cone system. You've got the blue and the green. You don't have the red. There is a rare type of color vision where the person only sees black and white. That's called achromatopsia or rod monochromatism, and it's very rare. Those people are also very light sensitive and have reduced acuity of around 2200 at best corrected. Okay? They have no cones. No cones at all, yes. Mm-hmm. No. Yes, question?
What about very rare cases of people with 4 cones?
There is. Tetrachromacy, that's right. There are some, and we're gonna get into that in just a second. I'm gonna show you guys. This is cool. Okay, let's keep going. All right, so here we go.
No cones would be perfect for deep sky.
No, it wouldn't.
Because you have the high acuity and
No, because there's other issues that unfortunately decrease the person's vision. How many colors do you see up here? I don't want to go through. You don't have to count it, but this is something you can do online. There's 43 different bands. Now you notice how, to me, this looks different than it does to you guys, okay? Your pattern up here, because of whatever spectral wavelengths your eyes are most sensitive to, you might see this band here of yellow. You might see 2 or 3 different shades in here, where some people only see 1 shade in there. So these bands are all the same width. They're all this width right here. But if you see an area that it's wider, that means your eye is not resolving that spectral. And so when you look into a telescope and you're seeing something on the planets and you're saying, oh yeah, see that red festoon there, that red blue, the other person looks and says, I don't know what the heck you're talking about. Well, this could be why. Yeah. Yeah, so most of us see only 1 in this area right here. Yeah. There's a pink band that really stands out for me right here. Some of you can see that, some of you can't. So.
How many are in the green?
So there's like 4 or 5 there. I mean, there's 1, 2, 3, 4, 5, 6, 7. 7 right there. Yeah. We're limited to some degree, yes. This is not truly a true test, but it does get you halfway there about. Okay, next one. Let's keep going. So here's another test. Take this online. This is really fun. Take your iPhone and Google igame.com, and you'll play a game, and what you got to do is it'll actually tell you how many colors, how good your color vision is. And if you can see a difference in the color, it starts out really easy where the difference is obvious. And it gets harder and harder until finally, this is about midway. Okay, this is midway here. There's like 10 more after this. All right? And you can see one of these is a little bit different color. Can you guys tell which one?
First row, second row.
That's correct. That's the one. This is the one that's a slightly, I put it in here so most of us can hopefully see that. But there may be some folks that can't. All right? Okay, let's keep going. All right, this is the typical one everybody sees. So if there's anybody in this room that has a red-green color deficiency, they will not be able to tell what number that is. Does anybody not see a number up there? I hate to put anybody on the spot, but usually there's one person or so. So everybody's got at least normal red-green color at this room. If you see a 21, you have a form of color anomaly as well. So that's a plate that we use to detect. Okay, so next slide, let's keep on. Color vision, yeah. Okay, so color vision, our eyes are designed to keep color constancy, okay, meaning that when the light gets dimmer or brighter as the clouds pass, you don't want your car changing from green to gray. You know, you want the color to stay the same. At least that's what our brain wants. And so it achieves that by looking at not only the true actual wavelength that's coming off of, but comparing it to the wavelengths around it and also to the amount of intensity that's coming. And your brain adjusts to keep the color constant. That's called color constancy. It's amazing to think about this, but the color of something is very, very dependent on a lot of factors. And it's amazing that our color vision stays as constant as it does. When it begins to break down is right around the time of twilight, when we're making that transition between color vision and monochrome vision, when our cones are beginning to go offline and our rods are coming online. There's a big difference there. And variable star observers notice that when they're looking at stars in telescopes that are red or blue. They may look drastically different brightnesses because they're at that transition zone between the cones cutting out because the cones need more light and the rods kicking in because rods don't need as much light. And in that transition zone, rods and cones both contribute to your perception of what color you're seeing. Yeah, Sherry.
I have a question about the rods. In normal daylight, are the rods saturated?
They're saturated.
How does your brain handle that saturation?
It's one of the amazing things that it does, vision processing, yes. It turns them off, basically. Yeah. Otherwise, you'd have a veiling glare that would be so bright. And that's the difference about the achromatopsia patient. The brain can't turn those rods off. And so they're extremely photophobic, light sensitive. They wear red glasses to kind of cut back on that. So.
Yeah, we talked a little bit yesterday about the purpose of white balance in the camera,
Yes.
because your camera's not doing that.
Your eye is doing that all the time. All the time. That's right.
And trying
Yep.
to understand something which you,
Yes.
through your entire life, has been automatic.
And bring meaning to it that's relevant to you. Okay, next, let's keep going. So remember this thing? Oh, I just throw that in for fun. I don't need to talk anymore about that. This just goes to show you how different our color perception is. Okay, next. This is cool. So take a look at this flag. Stare at this star right here. Right? And then when you're done, look, I should have put up something white, but maybe look around the room somewhere or down here. So count to 10, stare here and count to 10, then look down here. What do you see? Red, white, and blue flag, yeah. Again, because our brain is image processing. And when you're saturating your rods and your cones, and all of a sudden you change the background, it takes the brain a little while to figure out what's going on. And you get what's called a complementary color contrast or successive color contrast. And that comes into play in planetary observing. That's why the markings on Mars look green to some people. When they're sketching, they thought it was verdant vegetation because the rest of the ochre planet, orange, was color contrasting the dark mare and giving it a greenish tint. These observers were not fooled by anything. They were just responding to what their eyes were seeing. Okay, next. So normal eye sensitivity. This is incredible. Light and dark adaptation. This is where I want to get into some dark adapting. But think about it. Our eyes go from a bright sunny day to a dark starry night. That's about 100 million times variation in ambient lighting. And yet we can function in that for the most part. And that's due to something called dark adaptation. Our eyes are responding to the amount of ambient light continually as well and adapting to try to give us the best possible balance of clarity and sensitivity at all times, doing it without you even knowing it, right? A single photon of light can be detected by a maximally dark sensitized rod. That's phenomenal. That's as sensitive as CCD cameras in some cases. And the other thing the eye does is kind of neat, is the eye also takes into advantage of binning. It's figured out that, hey, if I link a bunch of these light-sensitive cones together, rods, I can see fainter. So the further away you get from the center of your vision, up to a point, the more rods there are. And the rods begin to group, they begin to hang out together, okay? They start grouping together, and 4 or 5 or 10 or 15 or 20 or 100 rods begin to sum together into a single fiber, and then that goes to your brain. So you're summing the effect of multiple light sensors, giving you that increase in sensitivity. What's the price you pay, though? Resolution. That's right. So at about 50 degrees off axis, your eye is like really sensitive, but your pixel size transported to the sky is about 20 to 30 arc minutes. That's how big your pixel is at that far out. You cannot resolve any detail smaller than that, about 30 arc minutes at that area.
So you're back down to about 2400.
Yeah, and even probably less than that, because now your ambient light is way down too. Your acuity drops when the less light you have.
You mentioned the size of the individual rods, in terms of microns. When they clump together, what's the kind of the biggest equivalent to a CCD chip?
Yeah, I don't know. I don't have an answer to that directly, but it's
Maybe millimeters?
no, not quite that big yet. We're still talking, maybe 100 microns, 200 microns, something around there. I don't really know for sure.
Repeat the numbers again, 15 degrees off.
So no, so about your cone, your rod sensitivity, the peak is about 20 degrees off axis in terms of the number of density of rods. Yeah, and it starts dropping down to around 30 arc minutes, 20 to 30 arc minutes. So if you're looking at something like out here, you can see trees and at night, and you can see gross figures of people walking in their tents and all that, but your resolution is only about half a degree.
More like half, center.
So in the center at nighttime, your resolution depends on a number of factors, which we're going to get into in just a minute. But it's much less. I got a graph I'll show you in just a minute here. Okay, let's keep going. Next slide. So let's talk about the things that can go wrong with your eyes. The most common, I said, tear film. You got to keep it good. Dry eye. Half of us in this room have dry eye. And it reduces clarity, it reduces contrast, and it reduces comfort. Your eyes are irritated. You're not going to be a great observer. You're just rubbing them and all that, and it's not good for you. So you want to go ahead and take care of that. So a good option is, if you are prone to dry eye, make sure you use good quality artificial tears, like Refresh or Sustain. These are good brands. Fish oil is amazing. High quality fish oil is amazing. It's a natural anti-inflammatory. It's great for increasing the quality of your tear film. Don't get the cheap stuff or you'll have fish burps, okay? And that's nasty. Get the good stuff, and it'll work for you.
Now you're saying you take it internally, not
Yes,
rub it on your
that's good point, Bill. Yeah, internally. If so necessary, your doctor might prescribe actual medicated drops, Xiidra or Restasis, to help with the tear production, yes.
Where might you buy high purity omega-3?
So you can go to a health food store, GNC, or online. The brand I recommend all the time is called Fortify, Fortifeye, and it's really good because it's a high purity, very potent, and I prescribe it to patients all the time, and it's amazing. They come back saying, I don't need my eye drops anymore because my eyes feel so much better.
Now we have to worry about cod depletion, though.
I'm not getting into that. Okay, so tear film, remember, it's the first thing that light from that galaxy is hitting. It's your tear film. It's not your cornea, it's your tear film. Okay, let's keep going. So another malady, this just goes to show you, this slide doesn't show very well, but this is a normal tear film. You want it nice and smooth. Look at these bumps and stuff. They look like, just granulated area. Obviously that scatters light, reduces contrast. Okay, keep going. Okay, you can have dystrophies of your cornea that are not really common, but they can occur. A lot of times you don't know it's there because it's been normal for your whole life and you don't realize you're not seeing as well as somebody else. But sometimes the cornea is clear and you look at them through a microscope, sometimes the person's cornea just isn't clear and there's nothing you can do about that. It's just the way it is. Some dystrophies that are superficial can be helped a little bit by using salt solutions that reduce swelling, because corneal dystrophies are associated with corneal swelling. If you can reduce the swelling, you'll see better. So the way you do that, you put a hyperosmotic drop in your eye or a solution that draws the moisture out by, osmosis. And it does help you see a little better. And certain kinds of contacts can help with that. Maybe even surgery is necessary if you have a real bad case. Okay, next. So this is what they look like. So this is the most common form of corneal dystrophy. It's called Fuchs dystrophy, and a lot of people have this. It's a granulated interior surface of your eye, little bumps. And what do the bumps do? They scatter light everywhere. Reduces your contrast sensitivity more than your clarity. And then this is what another dystrophy looks like. You can kind of see. It's just not clear. Okay, next. All right, cataracts. Intuitively obvious. If your lens is cloudy, you're not going to see as well. The surgery lens, we actually covered this already earlier. To reduce cataracts when you're young folks in here, wear sunglasses when you're outside. okay, with UV protection. It helps. If you're older, still wear sunglasses with UV. It might help. And of course, don't smoke if you do. You try to quit. Okay, next. So that's what a cataract looks like. Here's a normal lens. There's a cataract. So a lot of people think the cataract is on the front of the eye. It's not. It's in the eye. Okay, next. And this is what it looks like. Through a microscope, you can kind of see these kind of opaque spokes coming in. That would produce a star that would have spikes coming out of it due to diffraction. Okay, next. This is macular degeneration. There's two basic kinds, dry and the wet. Yes?
Just a little bit off topic.
Uh-huh.
I must have been History Channel or some other weird source. They're talking about in Roman times to operate on cataracts. What they do is take a pin and just detach the lens and just, I guess, float around your eye. Could that have been harmful?
It would have been harmful because there would have been infection rates that would have been very, very high. Two, when you take the lens out of your eye, and if it's just floating around in there, now if you don't replace it with something, you all of a sudden are now about plus 15 diopters hyperopic, which means your world is a complete blur around. The visual level that we call that is called hand motion. It's not 2400, it's not 20, it's about hand. You can see your hand waving, that's about it. And that might have been better if they had no light at all, if it was so dense. Maybe that was an improvement, but that would, of course, not be done today.
A little device, very thin needle, I would stick into the eye lens and just basically suck it out.
That's it, yeah, and that's what they do now. It's called phacoemulsification. Yep. So, so macular degeneration affects, unfortunately, the macula. That's the center of your retina. That's the part that you use when you're looking at things with high resolution. And it damages rods. It damages cones, basically. So you lose clarity, you lose resolution, you lose color vision to some degree, you lose contrast sensitivity. And there's two forms, the dry form, which is just atrophic age-related changes. There's no cure for that. There's no active treatment for that. And then, but that's not the bad form. Usually you can still have 20/40 to 20/60 vision. The wet, the bleeding, the fluid, the scarring, the wet form is the bad form. There is treatment for that, but it doesn't get you better. It gets you back to the dry levels if you're lucky. And that's where the blood behind the retina leaks in and damages it. Treatment, again, healthy lifestyle. Eat dark green leafy vegetables when you're young and when you're older. Don't smoke. Smoking doubles at least, some studies show, as much as 5 times the increased risk of developing macular degeneration. All right, next slide. And this is what it looks like. This is dry. This is where you're looking at Saturn, okay? This is your retina. You want it to look smooth and like this. Look at that. So obviously you've lost photoreceptors there. You're not going to see as well. This is wet macular. There's blood. That's where that red is. Okay, next. Glaucoma. I don't want to get too much into that. Glaucoma is damage not to the retina, but to the optic nerve that carries the vision to the brain. Obviously, if your wire is messed up, you cut your wire, you're not going to get the signal. That's what glaucoma does. Pressure increase in the eye goes up, causes damage to the nerve itself. The nerve can no longer conduct the vision impulses, and that's it. You're out of luck. Treatment is regular eye exams. You can't feel this. You can't see it at first. It's small. It's slow and progressive. It's dangerous because of that. So get your eyes checked regularly. Get your pressures checked. And if you do get it, we have drops we can put you on that lower the pressure down. Okay, next.
That was the first identified, I thought, used for medical marijuana. Is that true or?
Medical marijuana marijuana does lower eye pressure, but it's not very effective treatment. And there's 10,000 other things that you'll do before that, before we get to that level. In fact, it's even shown now that it's not as effective as they thought it was at once. Glaucoma affects the nerve. This is what the optic nerve looks like in your eye. It's a yellowish orange structure. It's got red blood vessels come out of it. And there's a center area that's a little bit lighter. That's the hole. That's all the nerve fibers diving down. It's like the vortex. If that hole gets bigger, that means you're losing nerve tissue. Here you go. That's a glaucoma optic nerve right there. Okay, next. So this is kind of what glaucoma does. Okay, this is a normal eye. Notice the clarity is not that much different at first. It's the contrast. You lose contrast sensitivity before you lose clarity. And contrast sensitivity is harder to detect. You don't notice it as much unless you're doing things like astronomy maybe. And you lose it from the side before you lose it from the center. Okay, next. So, okay, rods and cones. We've already done this. I don't really want to spend too much time on that. Let's keep going. Next slide. This is what they look like. This is a rod here. This is a cone. And light comes from this direction right here, from the bottom. The light-sensitive part of the cell, do you want to guess where it is? Is it this area down here, or do you think it's this area up here? It's this area up here. Yeah. See these little plates? These plates have photosensitive molecules in them called rhodopsin. And as the photon comes through here, this is the front of your eye down here. Starlight comes in. It passes through the cell body, the nucleus, the mitochondria. And then hopefully it is detected by one of these plates. And so you can see that there's a lot more chance of detection in a rod than there is in a cone because the plates are much more numerous. So that's why it's like a CCD.
We don't have a back illuminated.
So this is kind of like back illuminated in a way. It goes through the structure before it gets to the sensor.
What's the length? What's the depth?
So, just a few microns. This is maybe 15, 20, 25 microns here, and maybe 250 microns maybe.
There's a couple hundred wavelengths.
Yes, yes. And dark adaptation, when it occurs, results in maybe about a 10 to 100 million time increase in sensitivity of your eye. Okay, and the reason it does is because two things: your pupil gets bigger, okay, it lets more light in, but that only accounts for about a 16-fold increase. So your pupil goes, maybe from 3 millimeters to maybe 6 millimeters or so, or 2 millimeters to 7 millimeters. The bottom line is you only get about a 16-fold increase, and that occurs within about 3 or 4 seconds. Dark adaptation, to really get dark adapted, you want to spend at least 30 minutes in the dark. And even if you can go longer, that's so much the better. Because the rest of that dark adaptation is neurochemical. It's occurring in this area right here. And that accounts for a 6 million-fold increase in your light sensitivity. So that's the real process that helps us see at night. But yes, rhodopsin is building up. Yes, when light hits that molecule, the molecule undergoes a structural change which releases energy and then becomes light insensitive until it's regenerated. It can only be regenerated in the absence of light. That's dark adaptation. And the cones and the rods both undergo dark adaptation. So for the first about 8 minutes or so, your eyes are getting used to the dark. It's the cones that are adapting, not the rods. And then after about 8 minutes, your cones are fully dark adapted. Boom, then your rods kick in. So for the first 8 minutes, as you're adapting, you still might be able to see color. You're still getting used to the dark. Now, if it's really dark out and you're already below the cone threshold for color detection, you're not going to see color, but your cones are still adapting first, and then your rods do. And let's see, next slide. So there's about 100 million photoreceptors in your eye, 95 million rods, 5 million cones. And the density of the cones is most at the center of your retina. So here's the center, here's your fovea. So you're getting about 140,000 to 150,000 cones in every square millimeter of your fovea. That's the density that they're packed in there. And that density drops off very fast. By the time you're 10 degrees off axis, you're down to nothing almost. And that's why when you look away to the side of something, you lose resolution very quick because there's no more cones there. Your cones give you the resolution. But what happens is your rod density is the inverse of that. So your light sensitivity is due to this distribution. There's none in the fovea. So if you look at something at night, right at something, it's going to disappear if it's below the cone threshold in terms of brightness. You won't see it at all because there's no rods there. But you offset a little bit using averted vision, boom, now all of a sudden you're going to see it. And theoretically, the cones peak at about 15 to 20 degrees off axis. So that means theoretically, if you look 15 to 20 degrees off, you should be at the most sensitive. But in real life, that may not be right. It might be a lot less than that. It might be a half that because of the declining resolution of your cones as well.
Can you translate that into looking in the eyepiece, something, I don't know.
So think about your eyepiece, apparent field of view. Let's say you got a Plossl, let's say it's 40 degrees apparent field of view, okay? I know that's small by most of the eyepieces we're using today, but just for this argument. So it's 20 degrees to the edge, from the center to the edge, okay? If you have a 40 degree apparent field of view. If you're using a Nagler or one of these Explorer Scientific eyepieces, you have 80 degrees. So it's 40 degrees between the center and the edge. So you want to look about 7 degrees, okay? So 1/6 of the way, if you're using a 82 degree eyepiece, you want to look only 1/6 of the way from the center to the edge to get to about 7 degrees to get to be about this area of your retina. And you might experiment. You'd go a little bit further, go a bit less. It's up to you. They're your eyes. You got to figure out where that sweet spot is, okay? And then there's an area where there's no rods or cones. That's your blind spot. That's the optic nerve. And you want to make sure you don't try to put a galaxy on that spot. And it's 15 degrees to the right in the right eye, 15 degrees to the left in the left eye. So when you're using your right eye in a telescope, if you want to just avoid the blind spot completely, then what you do is you look to the right. And that way you don't worry about putting it on. If you look to the left with the right eye, at some point, galaxy's going to land on your blind spot and you won't see it, okay? Next. Here we go. Here's our CCD camera. That's what they look. This is an electron micrograph. Cones in the fovea, right here. Now these are not the same scale. Okay, these are cones here. As we move further away from the fovea, look at their density. It's decreasing. They're not packed up against each other anymore. Notice the rods, smaller, but none in here, many, many more in here. Okay, next. So again, in the fovea itself, you have rods and cones. I'm sorry, you just have cones, but you have three classes, red, green, and blue. Very, very few blue cones in the fovea itself. So your color perception when you're looking at something also is determined by your individual distribution of of cones in the fovea. How many red ones, how many green ones, how many blue ones you have. And it's different in everybody for the most part. Okay, next. And again, we can go on. This shows you how the rods are summed. Multiple rods form one input to the brain, so you can actually get binning. Okay, next. Well, we can skip that. That's just photomicrographs. Okay, so now let's get into a little bit of visual astronomy here. Now, this is out of Clark's book. This shows that if you plot the sensitivity of your daytime vision, what wavelength are you maximally sensitive to, it shows it, right about here, about 5,600 or so, and your nighttime is about 5,000 angstroms. That's called the Purkinje shift. Your night vision is a little bit more blue sensitive or green sensitive than your daytime vision. That's why we use red lights at night. So ideally, red light, our wavelengths is around 6,000, 6,200 in that area here. So what you're doing is you're actually using a light that the rods are relatively insensitive to, so you're sparing them their dark adaptation. But if you make your bright light too bright, you're still reducing your light adaptation. So you want to use as dim a red as possible. Bright red light's still going to bleach you. Yeah. At nighttime, your acuity goes down. Yes.
But if you're looking at something with red light, and your peak is in the green.
It depends on. It all depends on
Different?
your acuity depends on ambient light, how much background brightness you have, immensely. That's the main thing, is how much light you have.
One thing I think
Yeah.
about is if we really want to do night lights, it should be in the green area, but very much dim.
Your eye is more sensitive
Right, so you don't have as much
to
light.
green, but again, the green. But here's the thing: the rods are 4 magnitudes more sensitive to any wavelength than the cones are at any wavelength.
Right.
So even though you're using that green light, you're now closer to the peak of sensitivity of the rods. Now you're at that peak of the rod. So are you really doing yourself a favor? I don't know. I don't have the answer to that.
That's what I'm wondering.
Yeah.
Because it's red light, you have to get
Yeah.
fairly bright before you can really read.
So yep. So here it is. So maximum dark sensitivity. Your daytime vision. You pick up about 4 extra magnitudes when your cones are fully dark adapted, and then you continue to dark adapt all the way the rest of the way. So the first 8 minutes gets you right here, and then once your cones fully dark adapt, your rods start adapting, and they give you another additional 4 magnitudes. Actually, a little bit more than 4 magnitudes of sensitivity. Okay, next.
So,
Yep.
I was going to ask a question. If you're using your red light to look at an atlas
Mhm.
book, you're using your
Cones. Using your cones.
and you want to have the dimmest red light.
Right. Because your rods are still seeing that red light.
You want to keep it red,
Yes, because
not involve your rod.
because the peak sensitivity of the rods right here and here is shifted further from the wavelength than the green light. So the peak sensitivity of the rods is around 5,000, which is green. Okay, you want to stay away from that as much as possible, because you're going to be using your rods in 30 seconds when you're looking through that telescope. Your rods are still seeing that light, and they're still being desaturated, but not as much as they would be if you were using maybe a wavelength that was closer to that. So I don't know. That's why we use red lights. Okay, next. So this is dark adaptation. This just shows right here. Okay, time, 30 minutes, 40 minutes. This is your sensitivity. Your sensitivity is increasing as you go down. All right, this is how bright a light has to be for a person to see it. Notice the curves are biphasic. There's an inflection point right there. That inflection point is when the cones have fully dark adapted and now the rods are kicking in. There's no more cone adaptation after about 8 minutes here. And then after that, the rest of your sensitivity is the rods adapting. And they continue out to past 40 to 60 minutes. There's some adaptation that can occur as long as 2 hours. But you never get there in the real world because there's lights everywhere. The sky keeps you from getting fully dark adapted. These were studies that were done in dark rooms with nothing, no light. It wasn't under a starry sky. Our background is much brighter than what they were getting. So we never, even under these skies, never get fully dark adapted. Okay, next. Again, this is just a close-up. It just shows differences in your sensitivity of your retina. So this is basically the effects of averted vision. 0 degrees aversion, look at that. Your sensitivity is horrible. If you avert 2.5 degrees, look at that. You've gained already 2 magnitudes right there. If you go 5 degrees, 10 degrees, it goes down. So theoretically, up to 21 degrees, or 15 degrees or so would be the maximum.
Just to clarify, you're saying 2 orders of magnitude, which is 5 magnitudes.
Yeah, these are log based. So each of these is so that's 10, and that's 100 times right there.
And the factor of 100 is
Right,
5 magnitudes.
it's 5 magnitudes. Yes. And I was saying about 4 to 5. The cones get you, or the rods get you about 4.5 magnitudes of gain. Okay. So how do you maximize dark adaptation? Live a healthy lifestyle. Make sure you're not hungry. You don't want to be hungry when you're out stargazing. Eat well. Stay hydrated. Avoid alcohol if you can, because that suppresses the central nervous system, which is what vision is all about. Okay? You want to really, if you want to, cover your head at night when you're observing. That will help, because the sky is bright. As you saw, how many of you noticed you could see shadows of your hand the other night on Friday night? If they're in front of your chest, the Milky Way was casting a shadow. Okay. Some people say, well, what about pupil dilation drops? Or what about breathing pure oxygen? Okay, not helpful under these situations, unless you're at Mauna Kea. All right. Okay, next. Yeah.
So I have thyroid disease, so my eyes don't clear correctly at all. So if I use drops just before I go, would that?
Yes. If you have dry eye disease, yes, just before you start observing, and then maybe, depending on how your eyes feel, a few hours later. Yeah, just keep that tear film healthy, and then you'll see a nice contrast increase there. Okay, next slide. Again, contrast sensitivity, you want to keep that. That's what we just talked about. Keep your eyes from drying out. If you wear glasses with these high efficiency coatings on them really make a difference. They're called anti-reflective coatings. They help. And if you wear contacts, I'm a little iffy there. Contacts can help, but at the same time they can dry out. If they dry out in your eye, you're going to reduce your contrast sensitivity and your vision. Okay? So don't let your dry eyes out. Okay, next one. Okay, so learning to see. This is the part of the talk where Clark gets into really good. Your eyes are taking in so much information. Your brain is correlating vision and hearing and tactile and taste, all these experiences, and it's having to decide what's important and what isn't. And what you become aware of is what you decide is important for that particular situation. And when you're looking through a telescope, what you want to be aware of is the detail in that galaxy or that detecting that object. So you have to train your eyes. Now, what do you guys see in that picture there? This is cords of wood, yeah. It's not a fair test because it's a small picture. But the point is, this is you looking through your telescope at night at a deep sky object. The detail is there. You just have to learn to see it. You can detect it, but your brain has to learn to make it important, to recognize it. And when it does, you'll see that there's a cat sitting right there. He's big. I mean, look how big he is. He's not tiny. I was looking for a little tiny thing somewhere, maybe in the woods in the back. It's the same size as the log, but he blends in so well. Right? Okay, next. Oh, here you go. Let's go back one thing. This quote, let's see here. Did I have it? One more slide back. Here it is. Okay, so my quote. Okay, vision is a dynamic and continuous ballet between the eyes seeing something and the brain interpreting what that something is. That's in a nutshell what visual perception is. Another psychologist said, millions of items of the outward order are present to my senses, which never properly enter into my experience. Why? Because they have no interest for me. My experience is what I agree to attend to. Without interest, experience is an utter chaos. What that means is you have the potential to see a lot more than you think you do through your telescopes. You just have to learn to want to see it and learn how to see it. And how you do that? By practicing, doing it often and doing it regularly. Your eye can be trained just like your body can if you're a long-distance runner. Your eye can be trained the same way. Okay, next one. And these are the 2 books I grew up on. One on the left I have here. Actually, I have both of these here. They both go into great detail about learning how to see. Anybody have the one on the right? That's an older one. Tom Lorenzen wrote a great field guide back in the 90s, I think it was. And my kid spelled paint on it one day. And that's what that white is. So this is not his cover. That is house paint that got spilled on it that I couldn't peel off. Okay, so next slide. So these are the two books. Roger Clark's book right here, I highly recommend that. Let me pass it around. We can just start that and just pass it around and take a look in there. He goes into learning how to see. Basically, use averted vision, 5 to 10 degrees is what he recommends to the right or left of the object, slowly, observe carefully. You can try moving your telescope a little bit, which will increase contrast, because movement, our eyes are exquisite at detecting movement. If something moves off in your side vision, boom, you're gonna notice it, because it might be a leopard getting ready to eat you, right? So if you move that deep sky object in your telescope, it'll pop out, and when it stops moving, it might disappear. That might be, yeah, so just tap the scope and see it, okay? Magnification is very important. Don't be afraid to employ magnification when you're looking for deep sky objects, because your eye has to be able to detect the galaxy against the background sky. And when you magnify something that's not a star, this is not true for stars, but if you magnify something like a galaxy or the Orion Nebula, magnification does nothing to increase contrast between that object and the sky background. What it does do is it makes the object bigger and therefore lowers your eye's physiologic detection threshold for contrast. So by making the object bigger up to a point, your eye has an easier time seeing it and recognizing it. So you have to go to a certain power. Now, if you make it too big, of course, the brightness is going to be continuing to drop as you make it more magnified. Eventually, you lose that gain. So there's a sweet range of magnifications in there. And that sweet range is what Clark describes in his book. And I can't tell you, it depends on the sky, on your telescope. It depends on how the actual brightness of the object itself. But typically, it's about the range that you need to magnify to get the object to appear to your eye to be between 10 arc minutes and 1 degree in apparent diameter. Whatever that magnification is. So let's say you have the ring nebula, which is 60 arc seconds, and you wanted to get it to be 1 degree apparent diameter to your eye through the telescope. So you'd have to magnify it, 60 times. So theoretically, according to Clark, 60x will be a good starting point for you on this object in your telescope. And then go up from there and just see what results you get. And take your time. Okay. Sketch an egg. That's a really good device. An egg is featureless at first if you look at it, but if you look at it closely, it's filled with detail. Practice sketching. Drawing what you see in your telescope is probably the single best way to get your eye trained. It's the only way that I know of, other than just physically looking. But by doing that extra step of sketching, you observe critically. You become an involved participant in that object, and then you begin to gain a lot more skill quicker. Yes. Yep. It's the perception. It's your brain recognizing what it is that it's seeing and comprehending it. Okay. Next slide. We're getting close to the end here, I think. Is that it? Okay. So this is it right here. I'm not going to spend much time on this, but in a nutshell, if you understand this particular slide, this is Clark's whole book practically. And what it says basically is that as your size increases, okay, this is the size of the object, apparent angular size. Here's 10 arc minutes. Here's 100 arc minutes, which is like, a degree and a half, a little bit more than a degree and a half. Your detection threshold, the amount of contrast needed, more contrast here, less contrast here. So your detection threshold is getting better and better the bigger something is. So that means that up to a point, eventually the curves level off, which means that further magnification is not helpful. But up to a point, at any particular brightness of object, which these curves represent different brightnesses of objects, okay, or sky backgrounds, as he calls it in the book. At any given sky background, increasing the magnification up to a point improves your detection because the curves are sloping down. This is less contrast needed down here to see something. So don't be afraid to magnify something, okay? And said another way too, bigger telescopes are better. we know that. You can your eye's detection contrast, threshold detection is better at all ambient background brightnesses in a larger telescope. Because why? It gives you more light. That's the name of the game. Your eyes need more light to work better. The more light you give them, the better images you're going to be. So you need a bigger telescope. Okay.
The more you magnify something, it's the same number of photons you're spreading out across.
So there's Exactly right. And that's when you get to this side of the curve right here. Okay, you've magnified it too much now. Notice how the curves kind of flatten out here. Okay, down here, the object looks like it's a point. So you have you're not resolving anything. This is the range here in this zone here where magnifying it more does give you more detection threshold. It lowers your contrast sensitivity to the background sky and the object. By making it too much bigger, though, you then now get to the point where you don't have enough light to stimulate your rods effectively, and they drop off, and you don't see anything. So there's a sweet spot in here, and that's where you have, and it's typically between about 10 arc minutes, and in worse conditions, lighter sky or darker, fainter objects, you got to magnify them bigger. So you want to go somewhere between a couple arc minutes to a degree, somewhere in that particular range is the sweet spot, according to Clark. Okay, next.
It also gets a little bit into skylight filters because you'll be decreasing the brightness, but you'll be significantly increasing the contrast.
The deep sky filters work because unlike what magnifying an extended object does nothing to increase its contrast. It does for a star, a point source of a star. Yes, you'll see fainter stars if you go higher mag, because it does drop the surface brightness of the sky down without affecting the surface brightness of a star because the star is a point. But an extended object, that falls apart. Magnifying more in your telescope, that contrast is the same. You're magnifying, you're increasing the contrast of the sky by the same amount as the object. So you get no net effect there. The reason you do see better is because you're making the object bigger and your eye's detection threshold goes down. What a filter does is it does increase the contrast between the sky background and the object. Yes. 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 Yes, the less light, the less resolution. That's why a bigger telescope, you'll see more, because you're providing more light to your eye.
With regard to this contrast and the size of the object, if the object gets bigger relative to your minimum resolution,
Mm-hmm.
you're going to see it better.
That's right, up to a point.
There is contrast.
No, it's all about it. It's all about contrast. It's all that's the reason you can see detail in a galaxy is contrast. There's a contrast gradient that you're detecting, and that's what this is. This is not acuity. This is contrast. And the name of the game in deep sky observing is you want to increase that contrast detection level as much as possible. You want that detection level to be as low as possible. How do you do that? You experiment with magnification, and you experiment with eccentric averted viewing.
And I should also say you're involving more of the rods.
You're only using rods.
I mean, larger.
You're only using rods.
You're only using
Your cones are long gone. Yeah, this is all rod-related astronomy right here. Yes. Oh, yes. I'm sorry. Question here first.
How does exit pupil size play into that? I mean, if you're using a lower magnification eyepiece, you have a larger
Exit pupil is determined by magnification, so they're related in a way.
But I mean, does it,
Uh-huh.
because the whole thing, what you're seeing with your eye, the light coming into your eye is a bigger surface area.
So if your exit pupil is larger than your entrance pupil of your eye, you're wasting your
Right,
telescope,
wasting-
right?
but, I mean, if you're magnifying, you're going to a
Smaller exit pupil. So there might be physiology detriment. So if you have a cataract or you have a problem, you might accentuate those effects. But again, if you have astigmatism or farsightedness or nearsightedness, you'll minimize those. So maybe you can take your glasses off at higher powers because the exit pupil, as it gets smaller, becomes a pinhole effect.
You need to find, like, if you have a distorted issue with your eyes, then you have a smaller.
You might get around and get to a good spot. That's right. So again, experimentation. You own your eyes. You know them better than anybody else. Experiment. But keep in mind these principles. Okay, next slide. So let me just show you some things. We're almost done here. I sketch. This is as I was reading Roger Clark's book. I decided to sketch planetary nebulas, and so I went to unheavenly powers. Okay, so this was a 6-inch refractor that I was using, and I was at 700 power on all these sketches. I went way too high. I was at the point where I was in the curve where we were flat here. Okay, nonetheless, I thought the view was pretty nice. So don't be afraid to push the limit on magnifications, particularly if it's a high surface brightness object. Next slide. That's this is NGC 7027 in Cygnus. It's a protoplanetary, and it's a bipolar. And you could act with a 6-inch scope. I could detect that quite easily. And then in the central brightening of the star in this area. And I also had a daughter at that time who was 3 years old who loved to scribble, and she got to that. And that's what that stuff is there. That's not nebulosity. That's my daughter. Yep, who's 21 now. So, okay, next slide. Another view. This is, again, the detail you can see. If you spend time looking, some of these objects are quite fascinating at high powers. Also, what else, if you're using high powers, what else do you want to have in your sky? You want to be transparent, and you want to have good seeing. So think about that. Go back to that object several times at high power. You might find a night where the seeing is really good. You'll see things that you didn't see before. That has nothing to do with your own eyes' skill. It has to do with the environmental conditions. Okay, next one. And the next one will go. Okay, I threw this one at the last minute. So I'll read it in just in case somebody. So it's a plea for a break in the clouds. The gentle light of a distant galaxy must needs pour into mine eye, or I shall wither, bent and twisted, fall me down, distraught, to die. Tom Lorenzo wrote that in 1995, and I think it kind of applies to what we've had here, we've endured the past couple nights. Thank you all very much. Happy to be here. Okay. Yes.